In this lecture, I'm going to continue my conversation about variation. We'll get into inverse variation here, which is a little more interesting than just regular old direct variation, which you should have already watched or completed. The prerequisites for this will be a knowledge of solving linear, quadratic, cubic, square root, and cube root equations. Although people who watched the previous video did not see any type of solutions to quadratic or cubic equations. It's just that to be able to play around with inverse and direct variation in general, sometimes you have to solve quadratic equations or cubic equations, but they're the easiest kinds of equations of those forms. Also, I would like you to have a prerequisite of knowledge in direct variation as well. We'll start like we did with the with the direct variation lecture video. We'll start with a definition of inversely proportional. Two variables that are related to one another via some type of equation are called inversely proportional if their products are always the same, if the products of their corresponding values are always the same. That is, if you have an example where you're given a table of values for two variables, what you want to look at to see if they're inversely proportional, take a look at their products. So in other words, 3 times 1. Well, I see the product of x and y here is going to be 3. In the second row, we have 4 times 3/4. So checking that, the 4's cancel and you get 3. Next one, you have 5 times 3/5, and again, the 5's will cancel and you'll get 3. And finally, 6 times 1/2, which will also be 3. So these two variables, x and y, seem to be inversely proportional because their products are always equivalent. Now, what does this mean as far as variation? It just means that we have a couple variables that vary inversely as long as one of them can be written as k over the other. Okay, so in this case, we have y is equal to k over x. Now remember, with direct variation, it was k times x. Here it's k over x. And what I just mentioned in the last screen is that two variables are considered inversely proportional if their product is always constant. Well, if you take a look at this formula here, and if you multiply both sides by x, you'll get that xy is equal to k, where k is just some number. In other words, x times y is always this number k. So this works with our previous page here where we said for them to be inversely proportional, their products should always be some number. Now you see that that's what this whole sentence is saying, is that x times y is equal to some number k, where k is a constant. And we also call that the constant of proportionality. Okay, and then of course the last half of this definition here is just restating that k is a positive constant called the constant of variation or the constant of proportionality. As a first example, and usually when you're dealing with variation problems, it's always application examples, but they're the easiest kind of applications. They're actually pretty nice to kind of do. We have that older computer monitors produce a magnetic field where the effect of the field on the user varies inversely with her distance from the screen. So there's some type of magnetic field effect on your biology, in essence. And so that effect just depends upon how far away you are from the computer monitor. Now, these are old CRT monitors that I'm talking about. In an experiment, the field from a certain 13-inch monitor was measured at 22 milligauss at 4 inches away. So somebody was 4 inches away from, or maybe a measuring device was 4 inches away from this monitor, and it measured that the estimated level of the magnetic field was 22 milligauss. So what is that magnetic field strength at 10 inches away? So I've read this problem, I understand what's going on. Let me label the unknowns here. The two things we don't really know, the variables we're going to be using here, is the power of the magnetic field. So I'm going to say, well, I'll just highlight what I will label for one of the variables. So that first highlighted section there. I'll call that F. That's the strength of the magnetic field. And then let's see, what's the other variable we're dealing with here? Varies inversely with the distance. Okay, so this highlighted section right there we'll call D. We'll let D be the distance to the monitor. So we know that the strength of the field varies inversely. That means K over with the distance. Great. And now they give us some information. They always have to give us something, usually through an experiment, but they give us some piece of information. In this case, they say that the field strength is 22 milligauss, which I'll just write as 22, when the distance is 4 inches. So for this example, I'm going to assume that our distance D is always going to be in inches, just because it'll be different if in the next problem, let's say, that they state that you're a certain number of yards away or miles away or something like that. What does this imply about K? Well, I'll multiply both sides by 4 to find out that K is going to be 88. All right, so our actual formula for this situation is that, I'll clean it up right here, and I'll write it in blue so that it stands out, that the force of the magnetic field is going to be 88 over our distance away. The greater our distance, the less effect that that magnetic field has. So in part A, we just want to know how strong is that field when we're 10 inches away. So let's go ahead and write this out. The field is going to be 88 over, in this case, 10 inches, which will be 8.8. And we know that we're talking milligauss because that was the original measurement for the strength of the field. 8.8 milligauss. Now, we really have no idea how strong that is, what that really means. I mean, if somebody said, oh, that's 17 pounds, which doesn't make sense, but at least we'd have some idea of what that is. We have a physical representation. That's something we're used to. But milligauss, hard to imagine what that means. So part B steps in here. We have an elevated risk of cancer that can result from exposures to field strengths greater than 14 or 4.3 milligauss. That's just from some data that we kind of dug up. So if you know there's an elevated risk of cancer if you have greater than 4.3 milligauss magnetic field from this object, how far away do you have to sit from this monitor to reduce your risk of cancer? Okay, so in this case, they tell me the field strength is 4.3. So I'm going to go ahead and let F equal 4.3. That's the field strength that I'm concerned with. So 4.3 is equal to 88, and I'm concerned with finding the distance here. This is an equation with a fraction, so I can go ahead and multiply both sides by the LCD, which in this case will be just D. On the right hand side, the D's will cancel, they're common factors. So this equation will turn into 4.3D is equal to 88, and I'll divide both sides by 4.3 to get that D is equal to, actually I should say that D is roughly equal to 20.5. And remember, our D is in inches here, so I'll write inches. So to maintain a lower risk of cancer from using this monitor, you want to maintain a distance of 20.5 inches or greater away from the monitor. So about 2 feet from the monitor is probably pretty safe. That's what I kind of dig about the variation problems, direct and inverse, is that you can really learn some kind of interesting things. I try to take things that are actually factual here, but this next example is not so factual. The time needed to dig a hole. Now this is something that you would normally see in a general algebra textbook that most people really don't care about. To me, I think it's more interesting to see the physics examples that we've just been going through. But this example's okay, I guess, right? The time needed to dig a hole is inversely proportional to the number of people digging. In other words, you add more people to help out, it takes less time. Okay. So suppose it takes 2 people 4 hours to dig a hole. How long would it take 5 people to dig a hole? Okay, so the time needed, we'll call that t, is inversely proportional, which means k over, the number of people digging, which I'll call that n. And then they tell us, hey, by the way, it takes 4 hours when there are 2 people. Multiply both sides by 2, and you'll find out that k is equal to 8. So therefore, the time needed for a hole to be dug is going to be 8 over the number of people that you have digging. And so if you have 5 people, we would let n equal to 5, and you would get that t is equal to 8 fifths, which nobody likes time expressed as 8/5 hours. Instead, you would divide that in and say it's 1.6 hours. In fact, most people would say about a little more than 1.5 hours. And that's a very fast problem. It's because it's more of a textbook problem. Textbook problems are kind of boring and fast. So let's move on to the more interesting style of inverse variation problems. You have inversely varying with the power or a root, just like direct variation with powers or roots. The definitions are all the same. You can read them here. Y varies inversely with the square, cube, or nth power of x if y is equal to k over x squared, or k over x cubed, or k over x to the nth power. Same thing with square roots, cube roots, and nth roots. So you can pause this to look at this and digest it if you want, but I'm going to move on into an example. As a more advanced example, let's take a look at this problem, which combines concepts from both direct variation and inverse variation. Some people call this joint variation. It's not that advanced, really. You just have to get used to the language of it. The resistance of a wire varies directly as its length, and then also inversely as the square of its diameter. Now, let's talk about that for a moment. It seems like there are 2 types of variation going on. We're saying the resistance R varies directly with the length. And this is so far so good, actually. This is pretty good. It varies directly. It means k times something. However, it also varies inversely as the square of the diameter. In other words, inversely we start division and we have that diameter squared. So the true formula is this formula right here. This is a joint variation formula. You have both a direct and an inverse variation going on, but it's actually not so bad once you get used to it. You just, if it varies directly with something, that goes in the numerator, and it inversely with something else, that goes in the denominator. The k, the constant of proportionality, is always in the numerator. So let's use some information to find out what k is here. A wire is 1.2 meters long, so they've given us the length of the wire. Maybe I'll fill that in, or maybe I'll note it up above. This is going to be L. It has a diameter of 0.005 meters, so this is D. And it's rated to have a resistance of 140 ohms, so that's R. So let's go ahead and substitute those values in for R, D, and L. They told us the resistance is 140. The length of this is 1.2. It's meters, but that doesn't really matter for this problem. And then the diameter is 0.005. Remember, it's diameter squared down here. So we have one equation and one unknown. We can easily solve this out. And when I do, I get that k is roughly equal to, let's see, 140 divided by 1.2 times 0.005 squared, 0.003. Now that's very roughly equal to that. I rounded quite a bit. In fact, it's 0.029166666 on forever. So you might actually want to use that more exact value if you can, because it's much better to use unrounded values when you're doing calculations than it is to use rounded values. So they gave us all this information in this sentence right here so that we would have a way to find the constant of variation. It's just a measured value that they did. Now we're going to go ahead and find the resistance of a wire made from that same exact material. So in other words, it'll have the same constant of proportionality. But this time our wire is going to be 3 meters long and have a different diameter. So the resistance is equal to K, which we've just found to be 0.002916 on forever, times the length, which we're going to say is 3 this time, we have a different wire, divided by the diameter squared. Diameter in this case is 0.008, and again, squared. And when we plug this into a calculator, I get roughly, very roughly actually, 136, I'll say 137. That's rounded up. 137 ohms. That's just the calculator part of it. So that's called a joint variation problem, where you combine both direct and inverse variation. And it can happen that you have a couple things that it's directly varying with. That's absolutely fine as well. Everything it directly varies with goes in the numerator. Everything it inversely varies with goes in the denominator. Our very last example is going to be extremely advanced, but I think it's still doable. The ratio of the surface area of a cube to the volume of a cube is inversely proportional to the side length of the cube. So let's try to digest that. Let's actually draw a cube here. And I've just labeled the side lengths all S because it's a cube, so they all have the same side length. And what we're saying is the ratio of the surface area, so we could calculate the surface area here, to the volume, which we could easily calculate the volume as well, is supposed to be inversely proportional to the side length of the cube. So ratio is equal to K over S. The ratio is equal to K over S, means that it's inversely proportional to the side length. So let's see if we can figure out the actual formula here. First of all, the ratio itself, in the numerator we have the surface area. If you look at the surface area here, the area of the front of this box is S squared. It's just S times S. But how many of those sides do you have? Well, you have 6 of them. Okay, so that's the surface area, 6 times S squared. The volume goes in the downstairs here in the denominator, and the volume is just S cubed. Well, you can cancel things out and you get 6 over S. Oh, well, wait a second. R is 6 over X means that K is just 6. This is one of those rare circumstances where you can actually find K just by drawing a picture. So I happen to know that R is equal to 6 over S, so our constant of proportionality is 6. And what's interesting about this is you can actually graph this. You can actually have graphed any of the previous ones as well. But I want to show you what the graph of an inverse proportion looks like, rather than showing you the graph of direct proportions. Direct proportions, we know they're going to graph as a single line going through the origin. In this case, it's not going to be a line. It's going to be a graph of something like y equals 6 over s. And we happen to know that from a previous talk, and if you have not watched the video, I have a video on graphs of functions, base graphs specifically. But, oh, that's supposed to be an X down there. But if you watch that video, you'll know that the graph of y equals 1 over x looks like this. Okay? So the graph of 6 over x probably looks something like that as well. And as you can see right here, this is a graph of R, it's area over volume, surface area over volume, and the x-axis here is side length. So you can see here that this is a graph of 1 over x. Essentially, it's s over, or 6 over x. And as you change the side length, you can see that you just change your position on that. Okay. It's a very interesting one. By the way, it's also true that the ratio of area to volume for a sphere is also an inverse proportional relationship. So it's very interesting. Just know that when you go to graph an inverse variation problem, it always is going to have this look to it, the look like that. Okay? Because it's the right half of the 1 over x graph, or the positive x values.